Okay, so where did we leave off last time? Oh, right. So we were finishing off talking about well-ordered sets. And so the thing that we'll be using is the fact that there exists an uncountable well-ordered set. And so where I left off is we're constructing a certain particular uncountable well-ordered set that's going to be useful for us. So I defined what a section is. And then number 10.2, there exists a well-ordered set A having a largest element omega such that the section of A by omega is uncountable, but every other section is countable. So when you first hear this, it sounds kind of weird, but it's kind of like if you think about the positive integers, right? So the positive integers, if we added a omega to that, such that that was so we added a maximal element to the positive integers, right? Then the section of that maximal element would be countable, and every other section would be finite. So if you think of it that way, it's really maybe not that weird. That's the way I think about it anyway. So let's think about how we could go about proving that. So what we do is let's start off with, well, we know there exists an uncountable well-ordered set. So let B be an uncountable well-ordered set. And then we'll create a new uncountable well-ordered set, which is C, which is just 1, 2 product with B. Okay. So, and of course, we'll just use the dictionary order. Now, the reason why we do this is because we want to make sure that we have an uncountable section. Right, so let's start off with an uncountable. So some section C is uncountable. For example, 2 cross B, I guess, for any if you look at that element there, if we look at the section that comes from that, every element which is 1 cross B is going to be less than that. Since B is uncountable, this contains an uncountable set, so it's uncountable. Okay, so what have we got? We started with an uncountable set, and now we've proved that there exists a set that has an uncountable section. Okay, now let's consider the following set. So let's consider the elements of C such that SC is uncountable. Okay, so what have we proved? We've just proved that X is non-empty. So what do we know exists?
C is well ordered, so there's a small element.
Exactly. It's a well-ordered non-empty set. So therefore, it has the smallest element. And let omega then be the smallest element of X. And that does it, right? Because by definition, it's in X, so therefore it's uncountable. The section is uncountable, but every section of it, every other section is countable by the definition of being the smallest element. Okay. Oh, so hang on. So we've got to give what A is. Sorry, I haven't said what A is. So A is that section, and then we just throw in that element of omega. Sorry.
Is it possible that A ends up being just no?
Okay, so now we've now we've constructed A, and so S, the section of A by alpha is just S alpha, that comes from X, that's uncountable, but every other section of A is countable because every other element of A is less than omega, and then by the definition of smallest, it has to be countable. So there we go. That's kind of fun. So we're going to call it the minimal uncountable well-ordered set. And we'll also think of A as the closure of S omega, or the section S omega, which will, for reasons which will become apparent later on. So notice S omega doesn't have a maximal element, but A does, because that's the difference between A and S omega, is just throwing in that maximal element. And finally, if A is a countable subset of S, of that minimal uncountable well-ordered set, then A has an upper bound. And that's pretty straightforward, because if we have little a is an element of big A, then the section of little a is going to be countable. And so let A be and so now we just look at the union of A in A S A. And so that's countable. So it's being a union of countable sets. because right, A is countable. It's a countable union of countable sets, so therefore it's countable. But we know that this is uncountable. So there has to be some element in S omega which is not in A, and that A is then an upper bound. Okay, we're not saying anything about least upper bounds or anything. It's just an upper bound. Okay, so that's kind of like the set theoretic background we need for chapter 3. Chapter 3 is on connectedness and compactness, which are kind of like two really basic topological properties. And so in Calc 1, you've already seen topological theorems. And you probably didn't know, you probably thought they were calculus theorems. But for example, these two really important theorems from Calc 1 are actually topological theorems. The intermediate value theorem, right? That, you know, you've got a continuous function, then over some interval, the function takes every value in between its endpoints. Okay. It doesn't depend just on the continuity of the function, but actually depends upon the fact that you're dealing with an interval, and an interval is connected. So that's a topological property. Another really important theorem you might remember is the maximum value theorem, which says that a continuous function on a closed interval attains its extrema. In particular, its maximum. So remember, it's either at an endpoint or a critical point. Again, not just continuity, but it depends upon the topological property of the closed interval, the fact that a closed interval is a compact set. And so we're actually going to be proving generalized versions of these theorems, which hold for any connected topological space or any compact topological space. Okay, so let's first define connectedness. So before we define connectedness, we've got to really define what disconnected means. So a connected set is a set that is not disconnected. And it's a set is disconnected if it has a separation. So a separation of X is a pair of disjoint, non-empty, open up subsets of X whose union is X. Now, trivially, every topological space is a disjoint union of open subsets, right? The empty set and itself. But both have to be non-empty. So this is a non-trivial separation into disjoint open subsets. Okay. So, and then a space is connected if it does not exist as separation. So, important, it's a topological property. So, because it's to do with open sets. So if you've got, so if a space is connected, then so is any space homeomorphic to it. And it's quite easy to see that this definition is equivalent to saying that a space is connected if and only if the only subsets of X that are both open and closed are the empty set and the set itself. Right, because if you have a non-empty set which is both open and closed, then its complement is also both open and closed. So that's sort of straightforward. Okay, so we'll do the usual stuff. We'll go through what a property means in terms of the basic topological properties. So subspaces. What does it mean for a subspace to be connected? So if we've got a subspace of X, then a separation of the subspace is a pair of disjoint non-empty sets A and B, whose union is the whole set, neither of which contains a limit point of the other. That the space Y is connected if there exists no separation of Y. I don't know why I put that comment in. But yeah, the first thing is what we want to prove in our lemma. So, right, so we're talking about Y being connected in the subspace topology. So we have a separation, right? If we can do it into a pair of disjoint non-empty open sets, well, the sets are going to be open in Y if they don't contain a limit point of the other set. So let's see why that's true. Okay, so let's go in this direction. So let's assume that we have a separation of Y. Okay, so Y equals A union B. Why doesn't it contain limit points? Okay, so for any subset of a subspace, then the closure of that subset in the subspace is the closure of A intersected Y, right? By here, I'm talking about the closure of A in X. Okay, but if it's a separation, then A is also a closed set. So that means A closure of A in X intersected Y has to equal A. Again, it's a separation, and so A doesn't intersect with B. So in this case, here we get that B doesn't intersect with the closure of A, and so the only difference between that and that is that this is the limit points. So that is empty. So it contains no limit point. B contains no limit points of A, and of course, by symmetry, B contains no limit points of A. What about going the other direction? So let's say we have A and B being disjoint, non-empty, whose union is Y and not containing others' limit points. Okay, well, since it doesn't contain the others' limit points, that means that the closure of A intersected B and the closure of B intersected A is the empty set. So that means A and B are closed in Y. So that means we have This is also true. So this is what we need to show that A and B are closed in Y. But if they're both closed in Y, they're also the complement. Since one's the complement of the other in Y, that means they're also open in Y. Okay. So let's think of some examples. So any space in the indiscrete topology, of course, is connected. Any space with more than one element in the discrete topology is not connected. Okay, that's they're the trivial extreme examples, always good to keep in mind. Let's look at this second example. So it kind of illustrates what that previous theorem we had about limit points. So let's think about Y and Z as subspaces of the real numbers, right? So here we've got -1 to 0, union 0 to 1, sort of open at both 0. That's not a connected space, right? Because both of these spaces, it's a union of two subspaces. So this is a separation, right? Because these things are both open in Y. So it's a separation, so it's not connected. Whereas if I do it like this, this is still splitting it up into disjoint, non-empty subspaces, but now they're not open. For example, this guy here is not open in Y. Also, if we think about it from the previous theorem, 0 is a limit point of this set here. So there's two ways of showing that, that it's connected. And of course, this thing is really just the closed interval from -1 to 1 and just another guise. The rationals are not connected, right? Because all we've got to do really is take any irrational number A and then minus A that gives you a separation of the.
Why can you pick an irrational number?
Hmm?
Because A is not in the topological space. So how can you talk about those intervals?
Right, but what's the topology on Q? The topology on Q is the topology it gets from the real numbers.
Oh, so we're not talking about the order
I mean,
topology
this.
What about the order topology on the rational?
Okay, we can talk about the order topology, but this is still. I mean, this is. So let's say pi. I mean, this is still okay. So let's do it this way. Sorry, you're right. The Q such that Q is rational and Q is less than pi. Union Q in rationals such that Q is greater than pi. That's right. When I put it like that, I meant that the intersection with that with the rationals.
Each half of that is some kind of infinite union of open intervals
Yeah.
That's the point there.
So, so even though pi is not a rational number, we can still compare rational numbers to pi. And get it. So it's not a connected set. Yeah, given any two rational numbers, you can put it into, split them up into two disjoint things. And finally, here is a subset of R2. Okay. So it would split it up into two sets like that. This is not connected, right? Because each of these subsets is open in X. And each one does not contain a limit point of the other, even though it kind of seems like this is going towards 0, but that happens at infinity, of course, and so it doesn't actually happen within the set. Okay, how do we go about constructing connected spaces? So we need a useful lemma for that, which is that if we have a separation of a topological space and we have a connected subspace of that space, then Y has to lie entirely in C or D, right? Because, well, we just look at C intersected Y and D intersected Y, and that would give us a separation of Y into open spaces if they were non-empty. If both were non-empty, this would give us a separation of Y. So that means one of them has to be non-empty. So therefore, it has to lie in either C or D. So that's pretty straightforward. Yeah, that's that proof there. So one way, a useful way to construct a connected spaces is just forming the union of a collection of connected spaces that have a point in common. So why is this true? So all these are the same proof, right? You argue by contradiction. So you've got, so let's say we have a separation of the union of the subspaces. Fine. Okay. But we're told that there exists a P that lies in all of them. So that P has to lie in one of C or D. Well, let's say P lies in C, but since now you use the fact that each one is connected, and so each, let's say its union of A alpha is our collection of connected spaces, and P is in each A alpha. But that means if P is in C, then each A alpha is in C. That means the union of A alpha is in C. And somewhere I've used that previous lemma in doing that. Here's another one. Oops, that should have been A. That A be a connected subspace of X. And so if we have a subspace that lies between a space and its closure, then that space also has to be connected. Think about another way of putting this is just saying, if you have a connected space and you just throw in limit points, it's going to stay connected. And the same proof as before. Okay, so let's assume that B is not connected. So that means there's a separation of B. Let's call it C union D. Well, what happens to A? Well, A has to lie either entirely within C or entirely within D, because otherwise we'd have a separation of A. So let's say A is contained within C. Well, the closure of A is then in the closure of C. And so we've got some sort of squeeze going on which forces B to be in C as well. And again, somewhere I used 23.1. Oh, that's right. The closure of C and D are disjoint. That's what I used 23.1. The next one is a good one because I feel like it really gets to the meat of what a continuous function is. We think of it as, being really, it's writing a function and your pen never leaving the paper. And this is this theorem right here. The image of a connected space under a continuous map is connected. Okay, why is that so? So let's say we have some f from x to y. Well, if we replace that by g going from x to f of x, where it's just like where g of x equals f of x, then this is a surjective map. So without loss of generality, we can assume that the map is surjective. Okay, so we want to show that f of x, let's call that z, let's assume that it's not connected. So let's say z equals some separation. Okay, well, it's a continuous map, so therefore we can have a look at G inverse of C and G inverse of D. And by continuity, these are open maps. They're disjoint because C and D are disjoint. They're both non-empty because of surjectivity. That's where we need to assume surjectivity. So this gives us a separation of x. And so that's our contradiction. So that's not so bad. And the final theorem we have in this little run of theorems, a finite Cartesian product of connected spaces is connected. And the proof is not, so we're going to use theorem 23.3, which remember is that the union of a collection of connected spaces having a point in common is connected. So So we'll just have this little picture to help us. So let's consider this set Tx. So we're going to choose a base point A cross B. Okay. And so if we think about X cross B, this space here, that's obviously homeomorphic to X. Just a horizontal, that horizontal space slice is homeomorphic to X, so therefore it's connected. Okay, so it's connected, and if we choosing an X, if we look at X cross Y, that's homeomorphic to what this vertical slice is homeomorphic to Y, so it's connected. So this cross space here is connected because it's the union of two connected spaces, and it has the point X cross B in common. So we can appeal to theorem 23.3. So we've got all these cross spaces being connected. Well, let's just look at the union then of all these Tx's. We vary over all the elements of X. Okay, so it's a union of connected spaces, and A cross B is a common point to all those spaces. So therefore it's connected. Okay. So we've shown that the product of two connected spaces is connected, and then we can use induction for any finite product, right? Because x1 cross x2 cross xn minus 1 cross xn, right, is a product of two connected spaces by the induction hypothesis. Okay, so what we're going to finish up. What about arbitrary products? Well, it turns out that so this is really a death blow for the box topology, showing you how bad the box topology. R omega is not connected in the box topology, whereas R omega is connected in the product topology. And in fact, an arbitrary product of connected spaces is connected in the product topology. So again, this is this thing about how the product topology kind of acts kind of like finite products. So that's useful. Okay. So why is R omega disconnected in the box topology? Well, we have to come up with a separation. Okay, and so a separation, I claim, is if we look at the set of bounded sequences, that be our set A, and the set of unbounded sequences, that our set B. That's definitely a disjoint union and thing. So what are we going to prove? We've got to show that those sets are open. That's actually not hard to do. So if we have any old sequence, A1, that be a sequence, so it could be either bounded or unbounded, then consider the following. So A1 minus 1 to A1 plus 1 cross A2 minus 1, A2 plus 1 cross. Right, so this is what is, this is the ball centered at A of radius 1 in, what topology is this? This is in the soup supreme, yeah, like that. So that's a perfectly good open set, right? And well, everything in this ball, if A was a bounded sequence, it remains bounded if we add or subtract 1 from each term. And if A is an unbounded sequence, it remains unbounded if we add or subtract 1 from each bit. So around any sequence, we can put a ball around it. And so these subspaces are open. It's kind of weird, right? Of course, this doesn't work in the product topology because, right, eventually you have to get all R's, because only finitely many can be like this, and if it comes from any R, then a bounded sequence is going to include unbounded sequences, and unbound sequence is going to. So these two subspaces are not open in the product topology. Okay, now why is the product topology connected? And really, the proof for this can be generalized very easily for 3. So let's just do it for this. So if you think about it, we can inject Rn into, well, let's call it Rn twiddle. We can inject Rn into R omega, right, by just mapping, if we've got a vector x equal x1 through xn, then we inject it by taking it to x1 through xn, and then zeros ever after. Okay. So we can think of Rn as naturally as a subspace of R omega. So if we look at the union of all these Rn's, we get some space, let's call it R infinity. Okay, it's not R omega. So what is it? It's the space of sequences which are eventually 0. So there exists some capital N such that X sub I0 for all I bigger than capital N. Okay, so this is definitely not R omega. This is definitely some subspace of R omega, and it's a proper subspace. Now, what can we say about R omega, R infinity? Well, let's assume that we know that R is connected. We'll prove that next class, but we already know that. We know R is connected. So we know Rn is connected, right? Because it's just finite Cartesian product of connected spaces with the origin in common. Okay, that's good. So R infinity is definitely a connected space. Well, it turns out that R omega is just the closure. Turns out that the closure of R omega, closure of R infinity is R omega. And so then there's a previous theorem which we proved that since that's connected, R omega has to be connected. Now, why is it in the closure? Okay, how do we prove something's in the closure? So let's say we have some arbitrary element of R omega. So what do we got to show? So we've got to show that it meets, that any neighborhood of it meets R infinity. Okay. So let's have a look at a basis element containing A. So it's a basis element, of course, in the product topology. So what happens? Therefore, there exists an N such that Ui equals R bigger than N. So that's what it means to be a basis element in the product topology. But then if we look at, say, U equal to A1 all the way up to AN, okay, so we take the first capital N elements from our arbitrary thing here and then plug in zeros all the way else. This is an element of U, but it's also an element of R infinity. And that's it. So any open set containing A has to meet R infinity. So therefore, we've proved this thing here. And as I said, this argument here can be generalized to any other thing in the product topology. Okay. Okay, so we will now, next class, look at, oops, I'm gonna